So we did, we got through example 4 yesterday, right? Okay. So I kind of alluded to this yesterday. I said that sometimes we might pick our variable to be y, whereas all the examples we've done so far have been with x. You just have to make sure that when you integrate with respect to y, everything is y. So your upper and lower limits have to be y values. You have to have y as the variable. You have to have dy on the end. So either everything is an x or everything is a y. So I want to show you an example of why we might choose to do this sometimes. So I want the volume of the solid obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. So the key to understanding these problems is drawing a picture. X cubed, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. You guys remember this graph, hopefully? We've graphed it before. Negative 1 cubed is negative 1, negative 2 cubed is negative 8. Yeah. So if I pick enough points, I can kind of see what this looks like. Oh, I just missed my point there. But alright, so there's my cube function, but we're not talking about the whole cube. We have some extra stipulations here. Y equals 8. What is y equals 8? Yeah, it's a horizontal line at 8. Okay, so if you think about that, that means I'm stopping my graph here. I'm not going above that. What is x equals 0? That's a vertical line here. And this is a typo. That's supposed to say the x-axis. Sorry about that. So x equals 0 is this vertical line. And the x-axis. So that means I'm not talking about this piece down here. I'm only looking at that top part. That little section. So I know a few of you were kind of struggling with the rotating. Oh, nope, I lied. I do want that to be y-axis, sorry. That's what I'm rotating around. Sorry. So we are rotating this thing around the y-axis. Yesterday we were rotating around the x-axis most of the time. If you're struggling with the rotating, think of it as a reflection first. If I flip this across the y-axis, this will go here. This will go over here. So that gives me the other side of it. A reflection, though, is just like flipping it over. If we're rotating, we're getting a three-dimensional object here. So we have this kind of solid here. Can you guys visualize that? So it's kind of like a waffle cone, except a little more curved. Okay? So if I'm trying to find this volume, this is a problem where I would not want to integrate along the x-axis. Because if I look, this is at -2 and this is at +2, but the x changes depending on where you're at on this. You know, down here, these x's are -1 and +1. If you look back at your examples from yesterday, all of those were something flipped on its side. And so it was the y value that changed as we went along. The height was changing. But we had a definite starting and stopping for our x. When I'm looking at this one, it's my x value that changes. You know, here the x is different than here. But we have a definite top and bottom in this curve. So we're going to integrate with respect to y here. So when we do this, the bottom is at 0. What was my top, my highest y value? 8. Okay, since 0 and 8 are y values, this is a dy. Everything has to be in terms of y. If you think about a cross section, so if you take a section here, okay, we agree that would be circular. And so the area of a section is pi r squared. So the radius, that is from the center, which in this case is the axis, out. So what would you use for that radius? Well, it changes though, doesn't it? Down here, the radius is smaller than here. So we have to use the function. Now, I can't put x cubed in here. Why?
Because it's not a line.
Yeah, so what I need to do is take that equation and solve for x, so I know what to put in here. So the opposite of a cube is the cube root. So this is the cube root of y for my radius. And again, we have to use that as an equation instead of just a number because the radius changes depending on where you're at on that solid. Okay, so now we've done the hard part. We're ready to work with this. If you want, you can pull out your pi. A cube root is like a 1/3 power times 2, so that's a 2/3. So antiderivative, if you add 1 to your power, that's 5/3. So that means we need a 3/5 in front, from 0 to 8. I'm just going to go ahead to evaluate this. Can I pull out the 3/5 as well? So that's 8 to the 5/3, or that's like the cube root of 8 to the 5th, minus 0 to the 5/3, or the cube root of 0 to the 5th. So the cube root of 8 is 2. 2 to the 5th power is 32. Cube root of 0 is 0 to the 5th is 0. So then 32 times 3 gives us 96 pi over 5. Is that okay with this? So all of these problems we've done so far have something in common. We've formed all of our solids by rotating it around an axis, whether it be the x-axis or the y-axis. And so we're going to find out, well, we're only going to do a couple of them, but there are several different strategies for finding volumes. In all of our problems, when you rotate around an axis, what shape is this cross section? If you take a slab in the middle, what shape is this on? Yeah, every problem we've done, they have a circular cross section. And so when we set it up, we just have to do the area of a circle, which is pi r squared. Now that is not always the case that the cross section is a circle. That's just happening on what we're doing because we're rotating it around an axis. So as far as we're going to get this in this class, that will pretty much be, all of ours will be circular. But if you went on to take more calculus, you would see things where they were not always circular cross sections. So there would be different strategies there. For us, this is kind of easy. If you've noticed, all of them, the radius is just how far it takes you to get out to the function. So on every problem we've just done pi times the radius, which is the function itself, squared. And so that's how we've set up every problem so far. This actually has a term. This is what's called the disk method, because a cross section looks like a disk in this case. So I put the term now. I'm not going to ever say use the disk method to do this. I'm just going to say find the volume. But just for your information, that's what we're using here. Now, sometimes we have different shapes that happen. So we have other things that we're going to have to do. Let's take a look at this one. If I want the volume of a solid formed when the region enclosed by the curves y equals x and y equals x squared is rotated around the x-axis. How is this different than the other ones we've done so far? I gave us more than one function, didn't I? Alright, let's draw this. Y equals x. We know that's just a line 0, 0, 1, 1, 2, 2. Of course, that would keep going. What's y equals x squared? A parabola. 0 squared is 0, 1 squared is 1, 2 squared is 4, negative 1, 1, negative 2, 4. So what am I trying to find the volume of right here? I said the region enclosed by these. So, yeah, this little piece right here. Okay, so a good picture can be extremely helpful here. I drew the full graphs, but if I wanted to, I could even kind of zoom in on that little section. You don't have to do this, but I'm just trying to show you exactly what we have. So this is what we've got so far. That's what we found. Now, if I rotate that around the x-axis, if you're struggling with the rotation, think of it as a reflection. So I reflect this line down. I reflect my curve down. And then we're rotating that. So this is a solid here. What's different about this shape versus the other shapes?
Like it's got two.
Yeah. This is hollow in the middle. Everything else we've done has been a solid, where we found the volume of the entire thing. But this is maybe more like a true waffle cone where there's nothing in the middle. And we have to find the volume of just this outer edge, not that middle piece. Okay, so this is kind of like when we found area between curves. What did we have to do if we wanted just the area between them? We subtracted. So that's exactly what we're going to do here. We're basically going to find the volume of the outside minus the volume of the inside. You know, if you found the volume of that outside piece, you're getting all of this. If you find the volume of that inside piece, you're getting this. So to get what's between them, you just subtract. So would this be one that we could do with x or for y? Do we have a definite? Yeah, we have a definite starting and stopping for the x. It's the y that changes along the way. So my x values, this started when x was 0, and it ended when x was 1. So we'll have a dx at the end. All right. So we could set up two separate integrals, or we could actually just do it all here. The pi, both of them would have a pi, so I could even just pull that out if I wanted. We really just have to do the outside radius squared minus the inside radius squared. Do you guys get what I mean by that? So if we wanted to truly, okay, we're integrating from like 0 to 1. What's the outside function? That was the line, the y equals x. So it'd be pi times x squared minus the interval from 0 to 1 of pi times the inside was my parabola. But we know enough about integrals to know that if both of those are from 0 to 1, we could put them together. They both have a pi, so you could take out the pi, and then you just have to do the x squared minus the x squared squared. Okay, so you could have set this up as two completely separate integrals. I just put them together to kind of save ourselves a little headache. Does everybody understand how I got that? So if we want to evaluate, we could take out the pi. X squared minus x squared squared would be x to the 4th. So when we integrate antiderivative of x squared, so add 1 to the power, so you need a 1/3 in front. Antiderivative of x to the 4th, so add 1, so we get a 1/5 in front. Okay, so if we put in a 1, we get 1/3 minus 1/5. Put in 0 and we get 0. So 1/3, that's like 5 over 15 minus 3 over 15. So we get 2 pi over 15. Did I lose anybody? So what we just did right here is the second and final method that we are going to learn for finding volumes. It's when we have two functions, an outside and an inside. So this is another visual of what's happening. And so what we ended up doing is found the volume of the outside minus the inside volume to get the volume between the two of them. That's what's called the washer method. If you think about a washer, it's got a hollow center. So when you do the washer method, you just have to do the outside function squared minus the inside function squared. All right, so let's see if we get through one or two more. And then we'll probably stop for the day. So on this one. I want the volume of the solid obtained by rotating the region in example 6a, so the one we just did, about the line y equals 2. So I am changing some of this. So if you think about the picture we just drew, the intersection stuff doesn't change. And that is 0, 0, and 1, 1. We had our line, we had the little parabola underneath. Where is the line y equals 2? Yeah, that's the horizontal line. So if I wanted to rotate around that line, I didn't leave myself enough space, did I? Okay, so if I reflected across this point is 2 below, so it would go 2 above. This point's 1 below, so it goes 1 above. Okay, we have the line, and the parabola curve fell on the outside of it. So this one looks a little bit different here. It's kind of like a Christmas tree stand. You set it on the floor, it's hollow in the middle, it gets wider as it goes down. Now what happens when we rotate around something other than an axis? The problem actually gets significantly more difficult. When I set this up, it's the y value that changes. We have a definite beginning and end for the x, so we're still going to integrate with respect to x. So that's 0 to 1. And that's an x, so we're going to have a dx at the end. Alright, here's where it gets a little more tricky. So we have to do pi outside radius squared minus inside radius squared. Okay, the outside. It's coming from here and going all the way out. So the outside is actually taking me to the parabola this time, right? But we need an equation for that. We can't just say x squared, because x squared would put it here. I need to measure this radius. Let's think about that. From here to here is x squared. All the way up to here is 2. So how do you get the distance between those? 2 minus x squared. Then for the line, we're starting at 2 and I need to come down to this line. So what would that radius be?
2 minus
Good. Alright, so we have a lot of FOILing to do here. So if I FOIL this first one, 4 minus 4x squared plus x to the 4th minus, FOIL that one, 4 minus 4x plus x squared. If I distribute my negative, my 4's cancel. Negative 4x squared minus x squared will be negative 5x squared plus x to the 4 plus a 4x. So now we can integrate. Antiderivative of x squared would be x cubed, so we need a 1/3 in front. Antiderivative of x to the 4th would be x to the 5th, so we need a 1/5 in front. Antiderivative of 4x would be a 2x squared. Put in 1. Put in a 0, all of those are 0. So if I were trying to do this without a calculator, we could get a common denominator. So 8 pi over 15. So 4 problems for tomorrow. So double what you had last night.